Okay, so we start. Good morning, everybody. We start these lectures. We start this morning with a lecture by Anna McLeod. It's about stellar populations, stellar initial mass function, stellar feedback across redshift. So please, Anna, I leave you the floor.
Thank you. Good morning, everyone. I suppose it is a Friday morning, so I'm not too surprised to see only a subset of you here. I hope that you've been having fun so far and learning quite a lot. So yes, I'm going to talk about stellar feedback mostly. I was also asked to talk about the IMF, the initial mass function, but I do have to be very honest with you, that is not really what I work on. So I'll try and do my best to inform you about a couple of basic things. But really what I'm going to do is I'm going to keep stellar feedback, which is the main thing I'm concerned about in my day-to-day research, as the central theme, and then involve the IMF and population synthesis models around that. So on my title slide here, I have my very own version of the baryon cycle of galaxies, and it's slightly different to what you would typically see if you just Google it and look at the first hits on Google. And that's because there is this subcomponent there about dust production and dust destruction. I'm not going to talk about that too much today, but we will get into it a little bit. But I guess, first of all, let's see if this works. Oh, there you go. I want to thank the organizers for having me, for bringing me to this really beautiful place. And if you have not thought about your weekend plans so far, here's what I can recommend. There's this tower just about a mountain over there, which is beautiful. You can go there in about an hour and a half if you walk, I want to say, maybe an hour 45. Sunrise from there is absolutely stunning. I bet that sunset is equally nice. You can walk all the way to almost Spain from here. It's about 9 kilometers that way. I've done that one morning. So yeah, again, thank you for bringing me to this beautiful place. Okay, and before I start proper, I just wanted to introduce myself and my research in one single slide. So, as I said, feedback from massive stars is really what I'm mostly interested in. And I look at feedback on a range of different scales. So I work on the actual sources of stellar feedback, so the feedback driving massive stars, how they impact planet formation in protoplanetary disks and globules in star-forming regions in the Milky Way. I have done a whole lot of work studying how pillars and molecular cloud structures in general are eroded by feedback from massive stars. I'm also interested in supernova remnants because clearly these are the end of the lives of massive stars. How all of this influences star-forming regions in general and the populations that will form within them. But then, of course, all the way up to entire galaxies. So how does feedback influence how galaxies evolve? And then there is a clear connection that we need to make to simulations, but that is an entirely different talk for a different day. This is a subset of my research group. Some of these people have left and others have joined in the meantime, but this is the most recent picture, and I will be talking a little bit about some of the research being done by PhD students and postdocs and master students in my group. All right, so without any further ado, this is what I have in store for you today. First of all, I'm just going to give you a bit of a background, an overview of stellar feedback so that we're all on the same page. And by all means, if there are questions throughout, please stop me and ask. If you think that what I'm saying is completely basic and you would like me to be more or go more into detail, then also just shout and say this is all stuff we already know. Or if equally, if I say things that are very opaque and very obscure, stop me and ask me to simplify. Okay? So after stellar feedback and an introduction to this, I will spend a couple of words about what we have actually learned, observationally speaking, from feedback studies on spatially resolved scales. Because that will bring us to the next question, which is, can we actually use these observational results obtained on spatially resolved scales to say something about star formation and galaxy evolution in the early universe? And the only way to do that is to address stellar population synthesis models and talk about the IMF in a bit of a basic format. So that at the end, we'll move towards really trying to do that connection to, between the local and the distant universe, at least when it comes to feedback studies. All right, let's talk about stellar feedback then. Maybe this works now. Yes, perfect, okay. So what I mean when I say feedback, I mean the deposition of energy, momentum, and metals into the surrounding medium by massive stars. So those stars, canonically speaking, 8 solar masses or above throughout their lifetimes. And really what stellar feedback is, and here I'm getting back to this baryon cycle schematic, feedback is a phenomenon that acts on multiple scales, right? On the smallest subparsec scales of the feedback driving sources, up to the scales of galactic outflows that really drive star formation then within the galaxy and enrich the interstellar medium in the immediate surroundings. It's a multi-temporal phenomenon. It acts throughout the entire life of massive stars. It's a phase phenomenon because all phases of the interstellar medium are affected by stellar feedback. But also then, of course, this makes it inherently a multi-wavelength phenomenon, which means that we really have to go and get observations across the entire wavelength range in order to be able to observe stellar feedback from in all its different components. So it's quite complex. What does it act on larger scales, especially in dwarf galaxies? Feedback can be strong enough to reshape the dark matter distribution in these low mass systems just by expelling huge amounts of baryons from the galaxy. Of course, we know it drives the expansion of star-forming regions. It disrupts and photoevaporates molecular clouds, and therefore it regulates the formation of star clusters and subsequent generations of stars. It is the source of chemical enrichment. And on the smallest scales, it does have an effect on protoplanetary disk dissipation and therefore planet formation. So as you can see, it really acts on many different scales. Now, we say stellar feedback, but really that term stellar feedback is an umbrella term, right? What we mean with that is actually a series of well-defined physical mechanisms via which the stars interact with the ISM throughout their lifetimes. So you have, for example, ionization, stellar winds, radiation pressure, but also protostellar jets and outflows, which originate from the very young stars, the very young massive stars, as they are still actively forming and therefore accreting matter and launching these bipolar jets and outflows. Now, we call these 4 broadly defined mechanisms as pre-supernova feedback. Clearly, I have not listed supernovae there yet. And this is actually a very critical point that we're going to touch upon multiple times this morning. So these pre-supernova feedback mechanisms start to act as soon as the stars form, right? And then at some point, around the 3 to 4 mega-year time mark, we'll have the first stars go supernova. And then we can start to add in that feedback mechanisms as well. This distinction between pre-supernova feedback and supernova feedback, as we'll see, is quite important. I've listed a couple of references here for you, as well as the QR code to one of the references, which is a review paper that Melanie Chavance and Mark Comolds and myself wrote 2 years ago or 3 years ago. I'm actually unsure about the 23 right here. But anyway, you can scan the QR code and find that review where these feedback mechanisms are very nicely explained. Right. So as I said, feedback affects the environment from the subparsec to kiloparsec scales. Let me give you a couple of examples, concrete examples. So on the smallest of scales and earliest of time, we know, thanks to work by Adam Ginsberg, that very young, still forming massive stars are actually able to significantly heat the gas around them out to significant distances from the forming massive stars. And this is actually quite important, as we'll see in a couple of slides from now. On the scales of star-forming regions, so tens to hundreds of parsecs, and again, we'll get back to this particular plot in a minute, so don't look at it with too much attention at this point. But what feedback does on these scales is it really evaporates and destroys the molecular clouds around them to such an extent that we can quantify this and find that molecular clouds evaporate faster when they're exposed to more massive stars, so more photons. And then the largest of scales, as we've already said, star formation-driven outflows from galaxies has a profound effect on the systems that are launching these outflows, to such an extent that these massive, really mass-loaded outflows can shut down star formation within the galaxies just by gas removal. So basically, quenching from the inside. And here's the crucial point I want to make, which is we need stellar feedback. It's not just a thing that keeps me going and make me write grants and so on, but it's actually a crucial ingredient to our galaxy evolution simulations. And here's an example by Phil Hopkins. It's not the newest one. I'm sure there's more or better pictures to illustrate what I mean here. But what you're seeing is two simulations of a galaxy. One simulation has been seeded with zero feedback whatsoever. Okay, that's the one on your right-hand side. And the other one has been seeded with an unrealistic high amount of stellar feedback. Okay, just imagine this for now as like a button that you can turn up and down, say zero feedback, crank it all the way up, lot of feedback. So in the case of no feedback, the galaxy has basically exhausted its star-forming reservoir of gas and formed so many stars that there's basically zero gas left. While the opposite is true in the case of extreme feedback, the galaxy is actually just sitting there and not forming many stars at all. Clearly, reality is somewhere in between these two extremes, right? This is what we observe. Have I been modulating my tone enough? So the point I want to make is that we need to empirically determine what the right feedback recipe is, because otherwise we cannot simulate the universe and make it close to what we observe. Okay? So we need to know about the stellar populations that are doing said feedback. All right, so we have done this, of course, or empirically quantify different stellar feedback mechanisms over the last couple of decades. And what I want to do now is just highlight a couple of the most important results here. Right, so let me start with these pillar-like structures that you've seen already in the first few minutes of this morning. So what we've done is we have quantified the effect of ionizing feedback by observing the photoevaporative flow of these pillar-like structures. So these pillars are inherently feedback-driven. So think about pillars of creation in the Eagle Nebula, right? Printed on mugs and T-shirts and you name it. I can't go to a conference without seeing the famous pillars of creation in M16. Even if it's something about cosmology, they're still, they find their way in there. But besides being pretty, they're feedback driven, okay? They typically point directly back towards the feedback driving massive stars, which are shaping them into these structures. At the same time, they're not only being shaped by feedback, but they're also being eroded via photoevaporation, okay? So what we've done to quantify this effect is to observe pillar-like structures in different star-forming regions, so exposed to different amounts and different types of stars and star clusters. So here was our sample. So we have pillars in the Carina Nebula, the pillars of creation in M16, which we've imaged with MUSE back its science verification run, as well as a pillar in NGC3603, which is one of the most massive star-forming regions in the Milky Way. So with a little cartoon here, illustrate the fact that all of these different pillars are indeed exposed to different amounts of ionizing photons, right? With NGC3603 being the one that is by far being hit by the most photons. This is log per second, okay? So, yeah, I already said this. How do we measure ionization? Well, by measuring the photoevaporation rate of these pillars in different environments. And without going too much into detail, what we find is exactly this, right? The pillars that are being exposed to more photons, or this translates to either more massive or more stars, evaporate faster. You can compare that to analytical models, and within a factor of a few, the two agree pretty well, observations and models. But this is clearly only ionizing feedback, so it's only one of these mechanisms, and it's only feedback on small scales, and it's only feedback on small scales in the Milky Way, right? Really, what you want is a huge number of observations to properly statistically characterize feedback throughout different types of environments. And for this, the Milky Way is simply not the final frontier. And here's why. So first of all, imaging entire star-forming regions where feedback acts in, right, is prohibitively expensive. The image of the pillars of creation I showed you earlier is a mosaic of 9 MUSE pointings, and that took about 4 hours of telescope time on the VLT. But if you wanted to image the entire M16 nebula, it would be about 180 hours of telescope time. And as you all know, you cannot put in a proposal for that amount of telescope time, okay? So clearly it would just be one single region. Obviously, in the Milky Way, you're limited, especially in the optical, if an instrument like MUSE is your instrument of choice. You're simply limited by extinction because we're sitting right in that. But also, the Milky Way, in terms of how galaxies come, is just not representative of all the different types of systems and environments across the universe. So let me go into this a little more. So conditions in the universe are different depending on where you look, and they change, they vary with cosmic time. Take, for example, metallicity, right? We know that the early universe, and this is a plot from simulations, but obviously we know that the same is true coming from observations, that the high redshift universe was less metal enriched, right? So why would we care about this? What does metallicity do in terms of stellar feedback? Well, take stellar winds, for example. Stellar winds are line-driven, right? So if you have less metal lines, this means less momentum transfer, which means that you would expect weaker stellar winds at lower metallicities, right? Conversely, at lower metallicities, stars are hotter, they have higher photon fluxes, so you would expect higher radiation pressures from stars at these lower metallicities. So clearly, when you want to understand feedback, you have to take metallicity into account. So what we want to do then is quantify star formation and feedback under these different conditions. And what we do about this is to exploit nearby resolved metal poor galaxies to try and understand how feedback would act at high redshifts, which are inaccessible in terms of resolution. And again, I'll get into this throughout this talk. So how do we actually quantify feedback? Well, one of the things that people have been doing over the last, I want to say, 5 to 10 years is, okay, maybe more than 10 by now, but anyway, is to use these feedback-related pressure terms. I'm not going to go into detail about how these pressure terms are actually calculated. You can ask me later, or you can look up the papers that are referenced in the next couple of slides. But what I want you is just to conceptually follow along. So the pressure terms that we can calculate are the direct radiation pressure. So this is just momentum transfer of photons acting on the surrounding ISM. The dust processed radiation pressure. So some of these photons will be absorbed and re-emitted in the infrared, and that's that dust processed radiation. Then the pressure of that hot 10 to the 4 Kelvin ionized gas as it is expanding, and the pressure coming from stellar winds expanding from the sources. And here's what people find. Excuse me. So what people find when they quantify these different feedback-related pressure terms, and for example, plot them for individual star-forming regions, and plot them as a function of the size of the region of interest, is they find that different feedback mechanisms are relatively different in terms of their importance as a function of size. And the function of the size here really is a proxy for the age of the region. So smaller regions, those ultra-compact H2 regions, are a lot younger, and larger regions have had time to expand and evolve. Those are the older regions. So as a function of H2 region or star-forming region age, different feedback mechanisms have a different relative importance. So what you're seeing here is clearly that the pressure of the ionized gas is at very early stages, so in those compact stages of star-forming regions, less dominant. But it does start to become more and more dominant as the regions evolve. What is most important at those earlier compact stages is the radiation pressure, okay? So this is work done by Grace Olivier in a handful of star-forming regions in the Milky Way. But the same is true when you look at star-forming regions in the central molecular zone of the Milky Way, and this is work done by Ash Barnes. Now, the caveat on this plot in particular is that these data points down here to the right are actually not Milky Way data points at all. These are evolved H2 regions in the Magellanic Clouds, so in drastically different types of environments compared to those Milky Way ultra-compact, really young H2 regions. So clearly, this is not only a function of age, what we're seeing here on this plot, but somehow metallicity must play a role in there. But we're just not quite sure yet at this point of the talk what that role is. As I said, these are Milky Way regions in the central molecular zone. And if you look at the y-axis here, you can also see that pressure terms in general in this extreme environment of the center of the galaxy are typically a couple of orders magnitude higher. So again, environment plays a crucial role. Ash Barnes then also went on to use the FANGS data set, which I'm assuming that you've already heard quite a lot about this week. Is that true? Some people here clearly work on FANGS related data, but if not, if FANGS is completely new to you, please do stop me. So FANGS has observed 19 nearby galaxies with MUSE, and Ash has been going on about determining these pressure terms for over I want to say 60,000 H2 regions across these 19 galaxies. And the trend with H2 region size they find is always the same, okay? Right, so we can use these pressure terms to explore relations between feedback and environmental conditions such as metallicity is the point that I'm trying to make. So what we did then was to really try and dig into this with the highest spatial resolution in low metallicity environments that we could. So we used, again, MUSE to cover 2 giant H2 region complexes in the Large Magellanic Cloud. So moving away from the conditions of the Milky Way into these lower dust content and lower metallicity environments. And what I want you to appreciate here is that we have the spatial resolution to detect basically all of the massive stars here, one by one, not the clusters, individual stars. We can detect them, we can classify them, we can determine exactly how many of them are there and exactly, I mean, of course, given limitations of modeling and so on, what their photon input into these regions is. So across all of these individual bubbles in these H2 region complexes, we've detected over 60 O-type stars, as well as a handful of Wolf-Rayet stars. And I don't have time to go into all of the results from this study, but what we did by directly linking the individual feedback driving massive stars to the gas properties and gas kinematics is exactly what we kind of were already expecting from earlier results, namely that the expansion of these regions is mainly driven by stellar winds and the warm ionized gas as it is expanding and exerting that pressure onto the molecular clouds. While the direct radiation pressure, which is in blue here, is really subdominant. It's a couple of orders of magnitude lower. Of different feedback mechanisms in a different environment. But again, these are only a handful of regions in the LMC. How does this now depend on the environment? For example, if I go to the SMC or other locations in other types of galaxies. So again, I'm not going to have time to go into this, but a master's student of mine has been using the same methodology to connect individual massive stars to feedback in the SMC, and another master's student of mine has done work along these lines in the Milky Way. If you're interested, ask me later. So again, the LMC and SMC are just not the final frontier when it comes to feedback studies, just like the Milky Way, right? Instead of tens of regions with this level of detail, we need hundreds to thousands to, again, statistically characterize feedback. And the argument goes much, the same way. So this is 30 Doradus. It's about 40 arc minutes across. And if you wanted to image that with MUSE, you would need over 200 hours of telescope time. Yes, fair enough. The local volume mapper on Sloan 5 has now, I think, imaged the entire LMC at least, or getting there, close. But the spatial resolution is a couple of factors lower than what we get with MUSE, of course, which is adaptive optics supported on a 10-meter class telescope. But also, more importantly, this does not sample the environment of different host galaxies. It's just one satellite of the Milky Way, right? So the solution is to go to nearby galaxies beyond the Magellanic Clouds to perform these kind of highly resolved studies. So we've done that. We've imaged yet another galaxy called NGC 300, which is a galaxy at about 2 megaparsec distance, again, with MUSE IFU observations. And we've done this game of calculating different feedback-related pressure terms for all of the star-forming regions, all of the H regions that we detect in the MUSE mosaic, which I'm not showing here, but I'll show later on, covers about the entire central star-forming disk of this galaxy. So NGC 300 is a flocculent spiral galaxy. It's happily forming stars at not too high a rate. It has a very gradient. And what we find is that the pressure terms along that negative metallicity gradient actually increase, right? So both the pressure of the ionized gas, which are those blue-green data points up here, and the direct radiation pressure ever so slightly increase as a function of lower and lower metallicity as you go out into the outskirts of the galaxy. So one of these is intuitive, and the other one is counterintuitive. And I'm going to park this information with you. You can think about it and later tell me which one of these two trends you think is the counterintuitive one. Yeah? But what is important for the discussion of today is that these two, I'll go back for a second, is that these two feedback-related pressure terms allow us to, to conclude that in the outskirts of the galaxy, there is more feedback as opposed to the inside of the galaxy. And that's important. Remember, these are pre-supernova feedback mechanisms, because if you look at the handful of supernova remnants, we only covered 7 with this data set, but if you look at these supernova remnants and you infer density of the matter into which these supernovae have exploded into, you will find that where feedback is enhanced, so in the outskirts of the galaxy, the density of the ISM into which the supernovae have exploded into is lower. Okay, and this is a very important point. Why? Well, first of all, we already knew from simulations that if you put pre-supernova feedback into your simulation, you would expect the density of the ISM to be lower, because these pre-supernova feedback mechanisms churn up the gas, they push it aside, they create these bubbles, right? They kind of prep the environment into which supernovae explode into. Well, if you don't use or you don't simulate these pre-supernova feedback mechanism, the ISM density into which supernovae go off into is a lot higher. So why do you think this matters? Anyone? Yeah. Stellar outflows, can you elaborate? Yeah, so yes, so there's definitely an element in there that is absolutely true. So the key point is that for many years, galaxy evolution simulations mostly only included supernovae as stellar feedback. Perhaps some of them would include radiation, but most of them just seeded their simulations with supernovae in some, with some sort of prescription. But it turns out that if you don't include pre-supernova feedback, you can put in your supernova feedback, but you won't get things right unless you artificially increase your supernova rate, right? And that is because the impact of supernova feedback is different, whether if you have or don't have this early clearing of pre-supernova feedback. You have to think about it like so. If you let a supernova go off in a dense environment, it will basically be confined by that dense ISM around it. It will go, that's it. Supernova feedback is diminished in that case. While if you let a supernova go off into a less dense environment, it can then go on and disrupt everything, okay? All right. So a former PhD student, master's student of mine who's moved on to do a PhD in Leiden, Lucy, has extended this kind of work to really low metallicity systems, so dwarf starburst galaxies in the nearby universe, and really finds a nice trend, at least when it comes to the direct radiation pressure with metallicity, okay? Lower metallicities, lower direct radiation pressures. Okay. Let's see what comes next. Yes, okay. Right, so this was only NGC300, but we have since started to look at all the FANG's galaxies, for example. And what I'm showing you here is the direct radiation pressure gradient for the 19 FANG's galaxies plus NGC300. And what I want you to look at here is the fact that all of these different galaxies have drastically different radial behaviors when it comes to the direct radiation pressure. Some of them have a clearly negative gradient, which is pretty much monotonic. Others have kind of wavy behaviors, and others have positive trends. So you really have to go and look at a system in particular. You can't just make an assumption that feedback will behave the same everywhere. The environment clearly matters. So what we've done with this initial work is we've quantified, basically, what are the main drivers of the slope of the direct radiation pressure gradient, okay, and the curvature of the direct radiation pressure gradient in these 19 galaxies. And what we find is that the slope is mostly driven by how much dust there is. And this is intuitive, right? If you have a lot of dust to impart momentum to, that's what's going to drive your radiation pressure. But the curvature of this gradient is mainly driven not by a local quantity, but by a global quantity, which is the galaxy's stellar mass. Okay? I don't have time to go into this particular but again, if you're interested, do ask me later. But what we've then also done is used this information of what is driving radiation pressure in these star-forming regions in these 19 galaxies to try and predict what the slope of the direct radiation pressure will be. So you can do this multivariate regression. And I think this was the plot that I had on my one-slide intro on Monday, where we actually recover pretty well what the slope of the direct radiation pressure in a galaxy will be based on its global galaxy-wide properties. Okay? All right. So all of this was observational work. I don't have time or experience enough to go into what all the simulations are doing. And I'm assuming that Simon already did a very nice job in telling you all about feedback in simulations. So I'm not going to do that. What I'm going to highlight, though, is this particular result, which was on the archive a couple of weeks ago, which I find is really novel. It's something that we haven't really seen before. And this is what they did in this study. They took the known locations of known O-type stars in the solar neighborhood, right? We know where most of these massive stars are in a volume of, say, I don't know, a radius of 400 or 500 parsec or so around the sun. And they also took a 3D dust distribution in the same volume. So know where the stars are, know where your ISM is, and what kind of the 3D structure of that is, and then simulate how photons then propagate from these stars and ionize and exert pressure on the ISM, and try and see if we can what we observe. Okay, so that's what they did. They performed radiative transfer simulations based on these known initial properties. And they produced a synthetic H-alpha image of the sky. And it looks remarkably similar to the observed. And so I think that this is a pretty cool result. And it just shows how far we have gotten in simulating feedback. All right, so let's take just a moment to digest what we've said so far, and then move on to the next bit of today. Okay, so what we said is that stellar feedback is really an essential component when it comes to trying to simulate how galaxies evolve and form stars. Clearly, because of this, feedback becomes a cosmic time issue because galaxies evolve over cosmic times. And to understand the interdependence, because it really is an interdependence between the stars that are doing the feedback and the ISM that is affected by the feedback, we must know about the stars. However, the stars and the star clusters in the early universe are unresolved, and so we've resorted to these nearby observations to try and start understanding or possibly connecting the low redshift universe to the high redshift universe. All right, are there any questions at this point? No, that's fine. We can carry on. Okay, so the next bit I want to talk to you about is whether we can indeed now learn something about the early universe from these local studies. So the question actually is that we need to ask ourselves, can we learn something about the high redshift universe from resolved massive stars or star clusters in the nearby universe? So can we use local analogs of high redshift galaxies? But then the next question clearly is, do local analogs of high redshift galaxies exist? Let's see, who's in favor? Are there true local analogs of high redshift galaxies? Who thinks that these exist? Show of hands. Well, can I study this particular nearby galaxy and then say I've learned something about the high redshift universe?
Like the closest guess is the galactic center.
Yeah, is that a high redshift analog? I don't know. Do high redshift analogs exist?
Like there's a paper by Steve Longmore and
yeah,
Frederick
Longmore.
Yeah, on that. They claim that.
Yeah, so we all do that, right? Yes, we write papers about it, but mostly we use this as a justification in our grant proposals. Oh, we're going to the perfect analogs of the high redshift universe. But is that really true? Okay. Properties change as a function of redshift. So let's take a look at just a couple of examples, right? So there's a clear evolution with redshift of the star formation rate stellar mass relation. So lower redshifts, higher redshifts. Okay, so clearly that is already something that changes. The position on a classical BPT line ratio diagram changes as a function of redshift. So if you are a galaxy that is in the low redshift universe, you would probably be sitting somewhere under here. And if you're in the high redshift universe, then you're probably sitting somewhere higher there, okay? And this already raises a couple of flags. Let's take a look at this particular galaxy. This is NGC 5253. It is one of the most widely used analogs of high redshift galaxies in the nearby universe. It's got a stellar mass, about 10 to the 8 solar masses, a nice star formation rate of 1 solar mass per year. It's actually quite dusty, and it's very low metallicity. And if you compare its properties to properties of high redshift galaxies, it's actually quite comparable, right? There are systems in the high redshift universe that we know of that have really high dust contents. In fact, if you position NGC 5253 on a BPT diagram, it does actually quite, or match the expectation of high redshift galaxies pretty well. Go on. So maybe these systems do exist, and our grant proposal arguments are valid. But typically, there's still this metallicity dependence. Local analogs sometimes or often have higher metallicities when compared to their higher redshift component counterparts. But then there's also other factors to consider that we simply don't know the answer to yet, which is, for example, escape fractions. So from galaxies, do these change as a function of redshift? What are the dynamical states that might have been different in the early universe? So all of these are still factors of uncertainty. But assuming that these local analogs exist, what we want to do, is once that we've determined for one of them properties such as the age, the metallicity, star formation rate, star formation history, escape fractions, and initial mass function properties, to then pretend like we don't have the spatial resolution anymore, artificially push it to a higher redshift and say, there, I have now learned something about my integrated study. I can just directly translate that to a higher redshift galaxy. And the way you typically do this is by using stellar population synthesis models. So let's get into that a little. Right. So this is the part where I'm not the super expert on. Okay? I have extensively borrowed material for today from a collaborator of mine, Elizabeth Stanway, one of the main developers of BPAS, if you've ever heard that. So I just want to acknowledge the fact that many of the things that I'm showing today come from Elizabeth's work. Okay, so let's take step by step. So feedback, as we know, as we've seen, is caused by stars. I'm going to start really simple here. Okay? We need to understand stars before we understand feedback, any scale and at any redshift. And this is something that you can also read up on in another very nice review paper by Sam Geen in 2023. And I think at some point I also have a QR code for that. But if you want to have the reference, do ask me later. Now, assuming that we understand stars, how do we synthesize a stellar population? Right? So just to be clear, what we want, what the outcome of this exercise is, of producing a synthetic stellar population, is to be able to predict the integrated light, so the color, the spectrum, and the luminosity of a stellar population, and whether that's a star cluster or the entire stellar population of an unresolved high redshift galaxy. It doesn't really matter, but that's the exercise. That's what we need stellar population synthesis models for. Right? To do that, we need a population of stars, right? We need stars at these various different masses that are born approximately at the same time. So that's what we call a single age population, or over a range of times, and that's what we call a composite population. And to do that, we need to know about what types of stars at a given age there are, and we need to know about stellar evolution. So not only what types of stars, but also how all these different types of stars evolve during their lifetimes. So we need stellar evolution tracks. So this, as you can perhaps already tell from this slide, but it will get significantly more complex, I promise you, is a complicated thing to do. So if you start out with your stellar evolution tracks, you have your sun-like stars, your massive stars, post-main sequence stars, and stellar remnants, and all the things that make up a stellar population, right? What you need next is an assumption on the initial mass function, right? How many stars of a given mass are there in your population? So that's what's called the population synthesis. And what you end up with, once you have determined which initial mass function to use, is a composite stellar population at a given age. You can then, from there already, determine certain quantities, such as the ratios of different stellar types that you have. For example, ratios of different types of Orpheus stars. You can do HR diagrams, so Hertzsprung-Russell diagrams. You can determine what sort of supernova rates you would expect from this composite stellar population, and so on. Okay? Or what stellar mass of the population is, because you just sum them all up. But if you wanted to go a step further, then you have to invoke stellar spectra. So you need synthetic atmospheres or observed spectra of stars. You can put all of those onto your individual stars in your synthetic stellar population, and you can get to a synthesized spectrum of that stellar population. Again, it could be a star cluster, but it could also just be an entire galaxy, right? So from these composite spectra, then, you can do a whole lot of other property and parameter estimation. Now, this is not a novel thing. In fact, back in the 60s, this is what Beatrice Tinsley's PhD thesis was about. This is where stellar population synthesis really has its origin. I think it's pretty cool. We don't have time to read the entire abstract of her thesis, but I do encourage you to go back to the slides later and read it, because it is quite fascinating how, yes, we have done a lot of progress in actually modeling these things. And clearly, you know, we've got really powerful computational resources nowadays. But she thought about this and worked this out analytically in a high level of detail. And I think that's pretty cool. All right. So I like to put things into schematic representations. So you'll see a couple of versions of this now. Just to recap, right? You have a population of coeval stars. You assume something about the IMF. You end up with your synthesized stellar population. You can then get a composite spectrum according to either empirical observations or synthetic model atmospheres. But what you can also do is you can evolve the population. If you know about stellar evolution, you can evolve the population according to theoretical models. And what you end up with is this simple stellar population. But if you then also make an assumption on the star formation history of your system, you can end up with this composite stellar population. And this is just a different version of the next diagram that's going to pop up in a second. But just to say that what you really can end up with is the ability to do full spectral energy distribution modeling, full SED modeling. So if you combine your simple stellar population with an assumed star formation history, with an assumed metallicity history, you cook in some nebular gas, and you cook in some properties of the dust in terms of absorption and emission, then you can produce this full synthetic SED. And this is now much nicer represented by Charlie Conroy, where you see for one of these initial simple stellar populations, all the different ingredients and how you end up with this full SED modeling. And that is really important, because then you can infer key physical properties, rogue parentheses that obviously should close after the teal color, such as age, star formation rate, metallicity, dust content, and stellar mass of your unresolved stellar population. Okay, so it sounds quite powerful. But as we will see, there are significant caveats of actually inferring these physical properties from a synthetic SED. So if we then go thousands, we can see an uprising in more and more stellar population synthesis codes that have popped up, right? Here's just a list of them. I am absolutely not an expert on these. I'm just listing them for your own interest. So if you want to know more about these, don't ask me later. Go and look up the papers. But the point is that all of the listed ones here, which have been widely used in the past decades, is that all of them assume that stars happily live their lives as single stars. So they assume single star evolution. And this is a bit of a problem. Does anyone know why? Yep. You should not be answering. But of us grow up with two sentences that we repeat to ourselves when we brush our teeth in the morning and we brush our teeth in the evening and we wait for the bus when we go to the office and so on, which are most stars are born in clusters. Most massive stars are born in clusters. And then the other one is most massive stars are multiple systems, right? So that's academically at least. So in the next couple of slides, what we're going to look at is 3 key ingredients that you actually need to take care of when you want to use or want to produce stellar population synthesis models. One of them is binaries. Then we need to talk about nebular gas and dust. And we finally get to talk about the initial mass function. All right. So yes, many stars are found in binary systems. In fact, the more massive the star, the higher the likelihood of it being born in a binary or even, higher multiple system. So the fraction of stars in binary system increases with stellar mass, but also there are interactions between these binary stars, right? There can be mass transfer between them, there can be mergers, and so on. And this will affect how the system evolves. Going back to metallicity, the binary fraction, right, is also strongly anticorrelated with metallicity. So you have higher binary fractions in lower metallicity environments. So in our entire conversation about feedback, massive stars, function of time, function of environment, function of metallicity, binaries are also a function of metallicity. So clearly, this is all interconnected, and we need to think about all of these issues. So why do we need binary models? Let's go and look at this into a little more detail. So the spectra of young stellar populations are dominated clearly, right, by the most massive stars, the most luminous stars. So here you should think of feedback. Massive stars, feedback, right? And 70% of massive stars, at some point in their lives, will interact with a binary companion. 70%, that's very high. And as we've said, these interactions will change their fate, their subsequent evolution, right? So for example, these effects, or the effects of these binary interactions are actually strongest at low metallicities. So here you should think about the early universe, right? Stars become hotter once they undergo these interactions, especially at low metallicities. So we simply cannot ignore binaries in emission line galaxies, so in star-forming galaxies. So what does this mean in practice? Here, what it means, okay? So binary interactions, as we've said, mass transfer, common envelope phases, mergers, and so on, will lead to hotter, more luminous, and longer-lived stars. So if you don't account for binaries, you can overestimate ages, you can underestimate star formation rates, and you can misestimate stellar masses and metallicities. So you can see that this is a bit of a problem, right? So just in terms of ages, as an example, why is that? Well, if you just start with an observed SED, and you look at the blue part of the SED, you don't know whether that blue part of the SED is produced by young massive stars or luminous older binaries, right? So your age will be clearly affected if you don't know about or you don't include binaries, okay? So this simple schematic here, as soon as you include binaries in stellar population synthesis modeling, becomes a wee bit more complex. Okay? I don't think that we can go into all of these little purple boxes that have suddenly appeared on this slide, but certainly also we shouldn't, because again, I am not the expert on any of this. But as you can see, we have now added quite a bit of complexity to this exercise of producing a synthetic stellar population, right? You need to test for supernova outcomes. Not all massive stars will go supernova, by the way. You have to take into account stuff like rejuvenation, mixing, stripping, proper binary parameters such as the period and the distance between the stars, all sorts of stuff, right? But if you do that properly, then you can also do pretty cool science with it, because suddenly you have unlocked the potential of saying something about gamma ray bursts and gravitational wave chirp rates, X-ray binary number counts, and supernova disruption kicks. You can determine remnant masses and all sorts of stuff, okay? So again, the key point here is you have to include binaries in your stellar population synthesis model. So if you do go on about using SPS models, make sure that you use one that accounts for binaries. So there are a couple of these out there. Here are some of them. And clearly highlighted, just because I've been extensively borrowing from Elizabeth's slides, is BPAS, one of the leading binary stellar population synthesis codes out there, led by Jan Eldridge at UC Auckland. Okay, so that was binaries. Let's talk about nebular gas and dust. So if you want to fit real stellar populations, then you also clearly, because these real stellar populations will have gas and dust in them, you must include these in your models. Again, you should think about feedback here, because that is actually what the massive stars act on, right? So nebular gas and dust will absorb away some of the blue light, will produce nebular continuum, but also emission lines and far infrared emission from the dust. So the key parameters that you need to know about that go into these models are then the gas density, the hardness or softness of the ionizing spectrum, what kind of gas and dust composition is quite important. What's the ionization parameter, right? But also the exact dust grain size composition will matter, because that will affect the dust extinction curve. So again, you can see how this gets infinitely more complex, okay? So you have to rely on radiative transfer codes such as cloudy. You have to include these in your spectral synthesis. Okay, again, I'm not going to go into this because that would be a completely different lecture and I don't have the expertise to. So let's carry on. We're going to talk about mass functions now. Finally, the IMF. But before I move on, are there any questions about what I've said so far? No? Where's the feedback? So there is no feedback in the modeling in the sense that, or I can repeat the question. The question was, where in the modeling is the feedback? It's in terms of what we want to know about feedback, it's not in there. But what you do is the radiative transfer part, right? So you want to model the emission lines and so on. So well, yeah, the radiative transfer part is basically your feedback. But what I mean with that bold font feedback there is that when you think about feedback, when you want to understand feedback, then these are clearly things that you need to make sure you incorporate in your models, right? So if you go and choose an SPS model to do whatever comparison or parameter estimation from your observation because you're interested in feedback, then you must choose a model that includes these. Right? Okie dokie.
Anna's done a really lovely job of describing all of this. Just for the students, I just wanted to add that there isn't yet any of these stellar population synthesis models that include both binaries and rotation.
Aha.
Not a single one yet. So
I have, yeah. Yes, you're right. And that's also a problem. I have not listed rotation here. Yes, but fair point. Absolutely.
In the previous, I don't know if you, yeah. Do you only care about ionized gas, or do you consider feedback for your model in the molecular gas or the neutral gas in general?
Well, so again, feedback is a multi-phase issue,
Yeah.
right? But then that depends on your radiative transfer code and its abilities. So in theory, you would want to account for all of those things, right? But in practice, you're just limited by the tools that you've got at hand. Okay. All right, so mass functions. So there is a couple of different types of mass functions that you might want to think about when it comes to stellar population synthesis. So one of them is a stellar initial mass function. So that's the mass function at the time of the starburst that forms your stellar population. Then there is what we call the present day stellar mass function. So this is the mass function after you account for stellar evolution. So if you evolve your population. Then there's the field star initial mass function. So this is the mass function after you have then accounted for the fact that star clusters evolve and can dissolve and mix, and the populations start to mix, especially if your goal is to look at an integrated population of an entire galaxy, right? And then there's the composite initial mass function. So these are the galaxy-wide initial mass functions. So stellar cluster mass functions, and sorry, I think I repeated myself here. Anyway, composite mass functions. So when you have a star formation episode, call it a starburst, you will form a population with a wide range of masses, right? So we all know that we toss around the most used names here, right? We know about the classical Salpeter law, which is the single power law, but then there's also Chabrier, there's Krupa, and so on, and they differ. So what we're going to see next is that you want to actively think about what the effect is in choosing one initial mass function over another, right? So again, the classical Salpeter law is the single power law, and it can overpredict the number of low mass stars. So there is no cutoff at the low mass end, which is in fact included by other more recent laws, such as Chabrier and Krupa. So schematically, what do all of these issues that you want to think about look like? So one is the slope of your IMF, right? Is it salpeter? Is it steeper or shallower? That actually has an effect on the ionizing fluxes, right? Because if you push it up, if you make it less steep, if you make it shallower, it means that you have more massive stars, and that clearly will affect your ionizing flux. But what about just the number of massive stars? Again, if your IMF deviates from salpeter at the high mass end, this again, of course, will have an effect on your ionizing fluxes. But also, what if your high mass end is stochastically sampled, right? So we know, the IMF tells us that there are more low mass stars and not so many massive stars. So you are in a statistical regime when it comes to number of low mass stars, but you get into the stochastic regime when you get into the high mass end. And the stochasticity of the high mass end will again have an effect on the ionizing fluxes. It depends if you have 10 massive stars or 1 massive star, right? I mean, it matters. But then again, what about these low mass stars? What about the low mass star end of the IMF? And this will clearly affect your mass estimates. If you assume one or the other, or yet another scenario of that cutoff at the low mass end, you will end up with more or not so many low mass stars. And because there are so many of them, you can under or overestimate your stellar population mass, right? So all of these things that I'm trying to say here is you need to think about what kind of model you want to use for the purpose of your studies, okay? There's a brilliant review on the physical origins of the initial mass function by Patrick Hennebel and Mike Rudich. Here's a QR code if you want to look at that immediately. And their very first plot is this one, which is a compilation of all sorts of different observationally derived IMF slopes in the spirit of asking, is the IMF actually universal or not? Is it the same? Does it look the same wherever I look? Because again, going back to the fact that environments across the universe differ, this is an important question to ask, right? And here's what they, in the very first couple of pages of their review, they already tell you, right? So I'm going to read this out to you because they say it much better than I can summarize in my own words. So they say, studies that compare all of these different IMF models have generally found them to be similarly compatible with observations, as well as other parametrizations. However, it is not possible to draw a single curve through all the data points. So none of these models fit all of the data, but they all sort of equally fit the data in different ways, okay? And the strong hypothesis of a true initial mass function universality is unlikely. So if you use your stellar population synthesis model that has some assumption on the IMF for environment A, and then you want to use the same one for environment B, you might actually be doing the wrong thing. It's just, these are things that we don't know yet, okay? A lot more needs to go into developing these models. So again, let's take a moment to digest all of this. So are you using a stellar population synthesis model? You should ask yourself what it is that you're using it for. And you should ask yourself what the model does for these things. What does it use in terms of stellar evolution models? What does it use in terms of stellar atmosphere models? What does it use as an IMF? Okay. What does it use as an initial composition or metallicity of a stellar population? Does it include binaries or not? Does it do something about the nebular gas and dust assumptions? Maybe it doesn't include these at all, right? So depending on what your needs are, you have to carefully choose which model you want to use. Okay. So the last part is still going to take us some time. So I want just to take a moment here and see if there are any questions. This is all wildly opaque to you, pun intended. Yeah, there's a question there.
What's the relative importance of the different feedback mechanisms? Like, for example, can we simulate without dust and still have reasonable results?
So this is not exactly a question pertaining to this last part, right? So, okay. So can you just quickly repeat what's the relative importance of, okay, right? So in the beginning, I was showing plots, which I think Simon also already showed earlier this week, where people have quantified what the relative importance of these feedback mechanisms is. Now, yes, there are numerical works that simulate these different mechanisms, and the power there is that you can turn things on and off to see what the impact is of, for example, only having photoionization and no stellar winds, of having or not having dust in your simulation, and so on and so forth. But did you talk about that, Simon, or a little bit? But yes, so there, if the question was if you can simulate that, then the answer is yes, you can. Yeah. So for example, what you could do is have a look at the Starford simulations where they do a lot of this turning on and turning off things, and as realistically as possible simulate the formation of stars and star clusters in molecular clouds with different initial conditions. And yeah, Simon, yeah.
I would also say if it's purely a matter of the feedback and not something like cloud formation, you only need to worry about the dust if you're actually resolving the scales on which observationally we find that the dust, like the radiation pressure on dust, is important. So like the parsec scales that Anna was talking about earlier. If you're only resolving like 10 or 20 parsec scales, so whole clouds, then it's all supernovae and photoionized gas.
Yeah,
and you don't need to worry about dust.
Yeah, absolutely. So different feedback mechanisms act on different scales. So I listed protostellar jets and outflows there. Those clearly have, let's call it impact parameter, a smaller impact parameter than supernovae. So depending on which feedback mechanism you're interested in, it will act on different smaller or larger scales, right? Yeah.
About the IMF, you've shown the point. Is it possible to make a PDF, a 2D PDF of it? And instead of saying that we have a universal ones, we have a PDF of stuff that we should draw from in order to get our results?
Yes, that's a good question. I hadn't really thought about that, but perhaps, so you, a slope PDF basically is what you mean. Yeah, I mean, maybe it would be interesting to correlate the slope of the initial mass function in all these different environments with environmental properties, and then see what I mean. I bet people have started looking at this. I just don't know, honestly. Maybe it says in that review paper, and I just didn't get that far down in it. But yeah, definitely. That's how I would go on about this.
Thank you. Could you elaborate on what the most obvious effect of the inclusion of binary stars in a synthesized spectrum would be?
Yeah. So I can go back to that slide maybe, so because I listed the main effects. Let me see here, right? So the effects are actually quite important. I don't want to use the term dramatic, but it's almost getting to that point. So clearly it depends on what the scientific question is that you're asking. Are you wanting to use your synthesized SED to derive the stellar mass of your galaxy, right? Then you could be overestimating, or misestimating, depending which way you go, what the assumptions are. You could over or underestimate the stellar mass of your galaxy. If your science goal is to determine star formation rates, you could be drastically underestimating star formation rates. And then that has subsequent ripple effects because you will want to put your galaxy on a scaling relation plot, for example, right? Where does it end up? And then conclude stuff from that. So your data point will be shifted around in these scaling relation plots quite significantly if you get some of these steps wrong because you didn't include binaries. Does that sort of answer your question? Yeah. All right, I think maybe we should move on. So let's just scroll down to here. Okie dokie. So now what we're going to do is, so just to recap, right? We had started, after we talked about feedback a bit, we had started to ask ourselves, well, can we now use these highly resolved feedback studies to learn something about unresolved or higher redshift galaxies? Then we had this digression into stellar population synthesis models because that's what we need to perform that step. So now let's try and do that step. And here I'm now going to be a bit biased and show some of the stuff that my group is actually working on in this sense. But first of all, the key takeaway message from this should be that even once you have chosen your stellar population synthesis model, these models still need validation. And here's why. Okay, so if you start out your synthesis exercise with an age, a metallicity, a star formation rate, and a star formation history. You do your black box magic, and you end up with synthesized spectra of composite stellar populations, such as these ones here. You can say a lot about what the assumptions of all of these, or what changing these initial parameters does to how your spectral synthesis looks like. Okay, so using stellar population synthesis model in that direction. Okay, again, this is to, you can just tweak these things and see what effect it has on your synthesized spectra. Great. But if you want to use these the other way around, namely from your unresolved integrated observation, and you want to use them to infer age, metallicity, star formation rate, star formation history, then the exercise becomes a lot more problematic because there are significant degeneracies in deriving or inferring these properties from a fit, okay? Because you will have multiple models that equally well fit your observed spectrum. So stellar population synthesis models used in this direction, good stuff. Stellar population synthesis models used in that direction, careful, okay? This is where this validation, this ground truthing of stellar population synthesis models becomes really important. And this is what we're trying to do in my group. So what you want to do is you want to validate via an apples to apples comparison. So you want to take your beautifully resolved observations and your integrated observations, and you want to compare these to resolved and integrated models at known metallicities and known other types of spatial and environmental variations. And if this is unclear now, it should become clear in the next couple of slides. So what you want to do is you want to know what goes in so you can trust what comes out, and then really be able to perform this step in that direction with greater confidence. Okay, so part of this is, as I said, stuff that people in my group are working on, and we call it the Spatial Resolution Project. It has several different elements to it. Some part of it wants to study feedback on the scales of individual stars and individual H2 regions, but we also want to study feedback on the scales of giant molecular clouds so that we can spatially resolve star formation histories, measure them, and so on, and especially do this ground truthing, which I'm going to explain to you how it works in the next couple of slides. But then part of our project goes up to the kiloparsec scales of entire galaxies. So here the aim then is to quantify what is the effect of losing or gaining spatial resolution in determining feedback-related properties, and to do that step of connecting to the local to the high redshift universe. So the people in my group working on this are my PhD student Bjarki and my postdocs Braun and the Feng. And Braun is the one who is working on this ground truthing the stellar population synthesis models. So let's get into that a little more. So here's the workflow. Or at least I try to make a bit of a schematic representation of this, right? So you start out with resolved and unresolved observations. Remember, this is what we want to want to compare resolved and unresolved observations to resolved and unresolved models. Right. So our observations, which I've shown you throughout the previous set of slides, you know that we have observations of the individual feedback driving massive stars, or the individual stars making up a stellar population, and the gas and dust around them, right? So we have spectroscopy for these resolved populations, and we have photometry for these populations. Then we can use tools such as HOKI. So I'll tell you in a second what that is. And in particular, a bit of HOKI called the age wizard to determine ages of these resolved stellar populations. And we can use this code called match from the resolved color magnitude diagrams of the populations of stars, star clusters, determine ages, metallicities, star formation rates, star formation histories. Okay, so I talked about BPaths, right? These stellar population synthesis models that include binaries. And Héloïse Stevens wrote this really handy Python package called HOKI, via which you can, in Python, interact with all the BPaths models. So if you want to dig into that, Héloïse has written a series of really comprehensive Jupyter notebooks where you can learn how to use HOKI to get BPaths models and fit them to your observations and so on. Okay, so if this is something that interests you or is good for your work, then go and check out HOKI. I'll talk about Age Wizard in a second too. So what you can do next is you can pretend like you don't resolve these individual stars anymore, right? You take your nicely resolved observations and you just put an aperture around them, pretend like you lose spatial resolution. So you can take an integrated spectrum of that stellar population for which you have single star spectra for. And then again, you can use HOKI, but then also a different code called Prospector, or codes such as SLUG, which is Mark Krumholtz's code that synthesizes star clusters to determine on these unresolved scales the same properties, age, metallicity, star formation rates, and so on. But with the crucial point that you use these resolved, or properties derived from the resolved bit as priors to the unresolved determination of these properties, right? And this is really where the key is, such that you can use this workflow to do two tests, okay? You can test the validity of your model inputs, right? So this is when you compare observed versus model spectra, but you can also test what the biases and what the uncertainties are of your fitting routine. And this is how you ground truth stellar population synthesis models. So I want to go back to NGC300 for a second. And now I'm actually showing you the footprint of our Muse data cube, or not data cube, this is 35 Muse pointings actually in cyan there. We also have a comprehensive suite of multi-wavelength observations for this galaxy. But really, what I wanted to say is that earlier, no one shouted out when saying, when I said, this is a galaxy at 2 megaparsec distance. No one said, but wait a minute, at 2 megaparsec distance, surely you cannot use Muse to resolve individual massive stars, right? The argument was we need a statistically representative number of highly resolved single star observations in order to do these feedback studies. And yes, it is a galaxy that is not super close by, so resolving single stars is an issue, and I'm going to get into that in a second. I just wanted to highlight, it doesn't look as nice an RGB composite of that Muse field of view that we've got, and if you think about the equivalent of the FANGS galaxies, which are absolutely amazing, here you can see how much higher spatial resolution we get from this much closer galaxy, right? You can really resolve individual star forming regions in individual bubbles and remnants and so on. Okay, so we've used this data set for the resolve part. We can resolve individual stars. We have an HST footprint that covers the Muse footprint. So we have photometry for the individual stars, and we have spectroscopy for the individual stars, right? So this is an HST image of a region in the galaxy, right? And again, no one shouted out when I said individual star studies at a distance of 2 megaparsec, but it's because we have this high resolution HST photometry and now also James Webb photometry that we can actually perform what we call enhanced spectral extraction from the much lower spatial resolution ground-based Muse data. Okay, this is what the Muse data looks like. So there's blobs and there's stars. And there's blobs. But because we have stars, we can use the more accurate PSF fit of the HST data to resolve stars from these blobs, which is pretty cool. And this is stuff that has not been developed originally for the purpose of studying young star-forming regions. It's actually a bit of code that Sebastian Kamann wrote to use Muse in the very crowded environments of globular clusters, but it turns out you can very well adapt it to equally crowded regions, but because they're more distant in nearby galaxies. So again, with this accurate PSF fitting, you can enhance your spectral extraction from the lower resolution Muse data, and at the distance of 2 megaparsec of NGC300, you can resolve individual feedback driving massive stars. And you can do that for an entire galaxy because you have coverage of an entire galaxy. So that's what we've showcased in an initial study of 2 of these star-forming regions. So we've identified a bunch of O-type stars, as well as Wolf-Rayet stars in these 2 regions, where none of these were known previously. These are all completely new detections. Okay, so this is just a couple of the zoomed in spectra of the stars and some model atmospheres plotted over them. Here's a color magnitude diagram from the HST data. And all of these are the ingredients to the workflow I've been showing you to ground truth stellar population synthesis models. Okay, right, this is just to say that these are all new detections, and it really showcases that we can do these detailed feedback studies in nearby galaxies, okay? I'm almost done, guys. I know that you're tired, but I'm almost done, I promise. Okay, so now we've done the spectroscopy, we've done the photometry of the individual stars. Now what we do is we determine ages. And this is pretty cool because this rather new method of determining ages is really handy when you only have a handful of massive stars that you've been able to identify and classify in your regions. So this tool called Age Wizard basically allows you, I'm not going to go into detail how it works, you can grab the slides later and it's all very nicely explained here. But basically it allows you to use those couple of O-type stars that we've identified and determine with actual, pretty good accuracy what the age of the stellar population is, just based on those couple of O-type stars, right? And what we've seen when we've applied this to the NGC300 data is that, and compared to ages coming from traditional isochrone fitting, is that this traditional isochrone fitting actually underestimates the ages of up to 3 mega years, right? And that is the order of magnitude on which supernovae explode. So it's an important effect. And again, this was done with BPAS models that include binaries, right? So these single star models are unable to predict about 20% of the ages compared to the binary models that we've used here. And importantly, it's applicable even with a small sample size. Now, for this spatial resolution project that I've been telling you about, we've initially used NGC300, but we have a whole bunch of other types of galaxies in our sample also that we are using. All of these have IFU coverage as well as high resolution HST and now also James Webb data. And crucially, they really span different types of environments, especially when it comes to metallicities. Some of these are high metallicity, some of these are low metallicity, and so on. Right. Good. And at some point, we'll want to compare it to simulations. So this is what we haven't done yet. So we are not quite there at ground truthing the stellar population synthesis models yet, but we are getting there. And if this is something that you are interested in, if this is something that matters to your research, or if you have any kind of input, question, or whatsoever, please do get in touch. We are very open for collaboration and suggestions and so on. Okay, so if you want to get involved or if you want to help, just get in touch. And I'm wrapping up now. So can we learn? This was our question, right? Can we learn something from these local resolved observations about feedback in the nearby universe? Well, I think the answer is basically yes, okay? These nearby systems, which we call local analogs, are bright. That's great, because then we can easily detect them. We can use them to validate models, even if the low mass stars in the systems are not bright enough for us to actually detect them and to spectroscopically characterize them. We can use tools such as Age Wizard to determine ages and properties of star forming, of star clusters in these systems, and therefore then derive all of the properties that we're interested in these local high redshift analogs, right? Just as a reminder, the massive stars in them are the sources of feedback and produce these escaping photons and outflows and so on and so forth. Okay, so really what we can do is we can then try and do that extra step of relating to the high redshift universe where we lose the spatial resolution. Now, putting it all together, and this is how AI sees someone cooking up the universe. This is my almost final slide, okay? If anything, this is what you should hopefully take home, okay? So stellar feedback is the not so secret ingredient when it comes to galaxy evolution models. It matters. We need to know about it. We need to observationally quantify stellar feedback, especially pre-supernova feedback. We've talked about pre-supernova feedback and how that is important in regulating the impact of supernovae subsequently. Nearby galaxies turn out to be really quite handy to mastering this recipe of learning something about cosmic history of evolving galaxies. Right? But we require a cookbook, and this cookbook is our stellar population synthesis models. But be careful, because this cookbook might be really good for photos, but tricky for taste, right? So what you want to do is really taste test your recipes before you use them to perform any kind of meal preparing. Okay, and this is, I promise, my very last slide. I just wanted to take the opportunity to highlight this conference, which is going to take place in Switzerland next year, and which I think is going to be really relevant to many people in this room. So please do keep an eye on your inbox. We'll be sending an announcement about this soon, but basically it is about what we've talked about, right? It's about star formation feedback. It's about AGN feedback across cosmic time and environments. We want to talk about environments within galaxies, environments around galaxies, and how all of this changes across cosmic time. And yes, there's going to be lots of sun, nice food, equally to what we've experienced here, but really on time public transport, because it's going to be in Switzerland. So that's it. Thank you so much for having me.
Okay, so that there is time for a couple of questions.
Hi, thank you for the really beautiful talk and overview. So I have a kind of double question. So I know like recently, like yesterday, we talked about some of the high redshift DataBase results, and there's been some conjecture that maybe some of this could be caused by things like a top-heavy IMF, like the strength of feedback or efficiency of star formation. Can you briefly say basically what that means, and if the stellar population synthesis could help us more efficiently narrow down some of those possible causes of what we're seeing?
Yeah, yes. So that's a great question. It's a great point. Which goes into, we don't really know whether the initial mass function is universal or not, but probably it isn't, right? And in fact, I wasn't here yesterday. I was busy reading proposals and finishing this, so I'm not entirely sure what was talked about, but we believe that in the early universe, the IMF was top heavy, right? So there were more massive stars compared to what we see in the local universe. And so that clearly then means you have more of these stars producing more photons. And as I've shown in this rather unprecise schematic representation, that has an effect on your spectrum, right? Because you just have more photons available. So we definitely need to take this into account. And then this goes towards choose your model, your stellar population synthesis model well, so that it fits your purpose. Because if you use something that is tailored to the Milky Way, chances are that you cannot really, or it's not applicable to the high redshift universe. Yeah.
There are other questions?
What if you have, like, for example, more composite environment, like with the AGN, then would that also influence your stellar formation in a certain way and the stellar feedback?
Yeah, okay, so there is an entire field that looks at AGN feedback. And clearly there needs to be more conversations between the people who study AGN feedback and the people who only study stellar feedback, because the two are obviously interconnected whenever you have both acting at the same time, which is also why we want to organize this conference, or we are organizing this conference to do exactly that, right? So yes, AGN feedback is important. It is a thing. In the more massive systems, you will have to deal with that also. Yeah.
Yeah, because earlier you mentioned that you, when you have pre-stellar feedback, it would affect ASM and like causing your supernova feedback to be different.
Yeah.
But to AGN environment.
Yeah, so again, this is AGN feedback is not my field, so I don't feel competent enough to exactly tell you what all of the effects of AGN feedback are. But within a galaxy that has an active galactic nucleus that influences star formation within a galaxy to some extent, you will have regions where this effect is more or less pronounced depending on where you're looking at inside the galaxy. So the relative importance between stellar feedback and AGN feedback might change within the system depending on where your focus is on. I think Simon wants to say something, sorry. Yes. Absolutely, yes. And also the good news is that I thought I had to run off like right now to catch my flight, but it turns out it's only later this afternoon, so I'm around until after lunch.
So let's thank Anna again.
Thank you.